Hello everyone. So today we'll be talking about norm vector space, and I would like to give an overview of what we're going to be discussing. We'll be discussing vector spaces, norm vector space, p-norm, linear functional, and banach space. Before even diving into vector space, we would like to talk about vectors. What are vectors? Well, vectors are basically a mathematical object with two features. For example, we have this is what we see in image as usual. And why do we need to have vectors instead of just points? Well, for example, if you want to program a robot, let's say that you want the robot to move from one position to the second position, and let's say you want the robot to be able to bring a beer from the fridge to your couch, and you're so lazy, then basically you go from 1 1 to 2 2, right? But in this case, right, we're just seeing that if you're feeding this information into the robot, or let's say a program, well, the robot only knows that you're only giving the location of those position. But what if we use vectors and tell the robot to complete what we wanted to do? So that's a different case, is that you have two different positions, but you have a vector that pointing to that second position, which tells you the robot, say that if you robot is in 1 1, then you're basically telling the robot to move into this, face into this direction, and move this amount of distance so that you can reach 2 2. So that's the kind of necessity of vectors. So now that we have discussed about vector, we can talk about what's a vector space. Well, vector space are simply, as you guys know, that it is just a space. In simpler words, we can say that it's like a playground where you can play around with vectors by adding them or editing to create a new vector and stretching or shrinking them using numbers. And you result in the same playground. So I should have said in with the visual image, but the visual representation looks like this. You have a vector space, and say that you have a single vector x, another vector y, and you try to add these vector and you get another vector. And this is what we have discussed in this definition, is that this is what we're telling here, is that if you add two vectors to create the new vector, which is our x plus y vector, this vector, it still ends up in the same vector space, in the same playground. So when we say that the vector does not end up in the same space, well, visually we're talking about that x plus y will end up in this location. So the second one also says the same thing, is that you may stretch it's not saying the same thing, but the second one basically says that it stretch or shrink the vectors using the numbers. So let's say you have your x here, x vector, and you want to either stretch them, right, using a scalar. So let's say stretch by a factor of 2, and you can also do the same thing, that you want to shrink the vector back to its original size. Well, in this case, what the second point is trying to tell you is that if you stretch or shrink a vector, it still ends up in this space right here and does not end up in outside the space, then we cannot, then the second condition will not satisfy. So this is what a vector space, basically what we're saying is it's a playground where you kind of add and shrink, add them, create a new vector, stretch, shrink using a number, and then the results still end up in the same playground. And the definition also says the same thing. You see that the vector space is a set over a few, which means you have a set there, you're trying to use some numbers, you're trying to pick some numbers from the field and try to do some operation which we call addition and scalar multiplication. And so next we will go on to what we call a norm vector space. A norm vector space is very simple. In a simple idea, what we're trying to talk about here is that if you look back to this picture right here, is that a vector space is basically you can add or scale some vectors and end up in the same space. But norm vector space, what we're saying here is that we have a vector space right here, but we have an extra two called the norm, which we denote like this, which basically says we can have an additional two to measure the length of the vectors. So you can measure the length of this guy, and you also can measure the length of this guy right here. So that's the whole idea. You get norm vector space is just basically you have an extra two that we call the norm, and you add the norm into the vector space, which makes the vector space become a norm vector space. And before even we talk about norm vector space, we have to define what is norm on a vector space. So if we read through this passage right here, a norm on a vector space X is a real value function denoted as the norm of X that satisfies these properties for all X and Y, which belongs to X, and A, which is from a scalar which is from a real value. And the first one, it says that the norm has to be non-negative. And the second one, what it says here is that if we have a vector that its norm is 0, then basically the vector itself, it has to be the 0 vector. And the third one right here, and that we're talking about, is if we scale the vector and then take the norm, it's going to be equal to the absolute value of the scale times the norm of the vector X. And the fourth one is basically trying to make a condition which it's what we've seen in our usual triangle inequality. And that's what we have been discussing. So let's go on to talk about some example of norm vector space. So as I told you, like in previously, norm vector space is basically a vector space with a additional two called the norm built into it, or we can call equip. So let's see an example. Is R with a norm as the absolute value a norm vector space? So that's what we have put it in mathematically. We set our vector as our real value, as our real line, and our field also as a real line, and we set our norm to be the absolute value. So first we need to check that R itself, is it a vector space? Well, it is, because it satisfies the definition 1. And our definition 1 basically says that it has to satisfy these two properties right here. So if you put it like if you think about it in a visual way, what we're saying here is that we have real line right here, and if you try to pick any number, right? You pick x. If you pick x and y, pick two vectors, and then you want to add them, and you result in x plus y. Well, this guy right here, it still ends up in the real line. And if you do the same thing, let's say if you do apply the second condition, where you say that if you scale a vector and it still ends up in the same space, well, that's basically the same. If you do this, then we say that, well, if you scale this guy right here, it's gonna still end up in the same line right here. So, well, you can do this like, what we're seeing, what I'm trying to tell you is that if you do this, if you pick any number and you add them, well, you're still gonna, no matter how many times you do it, or how many different ways you pick it, right? It's still gonna end up in the same space, R. So R is a vector space. So let's try to check whether absolute value is a norm. Well, because our norm is defined as the absolute value, and the absolute value, well, what it does is basically you take a number. If it's positive, you just leave it as it is, and if you have a negative value inside the absolute value, then you're just gonna you're gonna multiply by -1. So in both cases, we get greater than equal to 0. So which satisfied our first condition. And the second one is also the same idea, is that, the only way that you have, if your norm is defined as 0, then if you apply your definition right here, this means that the absolute value is 0, which means the only way that you can get your absolute value to be 0 is the x is in the 0 itself. And as you can see, the third one and the fourth one is the same idea. The fourth one, what we're trying to do is we write the definition of the norm, because we define our norm to be in this way, and we use the triangle inequality, this property, which is from your real space property, and we just rewrite your absolute value of these into the norm definition. So that's the first example. And the second example is almost the same idea. What we're trying to do is you try to take the vector space and you check where that vector space is actually a vector space, and if you have the norm, then you need to check the norm actually satisfy the definition of the norm. So we have a vector space which in R2, the norm is defined as our usual Euclidean distance, and as so right here 1 to 4, we're doing the same thing, is that we take a norm and you have your Euclidean distance, and if it's greater, this is going to be greater than 0, because the inside will always give you a positive value. And this is the same idea right here. What we're saying in the second one, it's basically saying that if your distance is 0, which you're saying that you're not even moving away from your origin, then the only way that you're talking, the only way that your x and y, it's gonna be end up in 0. So this is the same idea. I won't really discuss on too much on these things. You apply the same idea. What you want to do is just end up being in this guy, end up in this side, so which you satisfy the definition. And the fourth one is a bit kind of need a little more trick to prove it. But I would like to also kind of add on to say that, well, in what kind of situation that we can have 4 to be not satisfied. So let's just write out what does it mean by not satisfying. So which means this guy is not going to be, this guy right here is going to be greater than this guy right here. So if we, let me just remove this guy, and if we happen to have something like this, right, if we draw it in our map, let's say we put it in a visual way, you have your x right here, let's say x vector, and your y vector, and then you want to add these x plus y vectors, then you get x plus y. Well, this is the case that when both of these vectors are the norm of these vectors, or let's just call the size of these vectors, it's going to be always greater than this guy. But if we have something, let's say that this doesn't satisfy, in the case what we're talking about is really talking about the vector of this guy. It has like some kind of jump, right? And if we really talk about the distance that doesn't follow in a straight way, well, what we're trying to talk about is we're talking about something that close to differential geometry. So we can say that what differential geometry is talking about is that we're talking about we have two positions, let's say A and B, and it says that the length of the path is path dependent, which means it's not, we're just saying that it's not in the length is not just the distance of between two positions are not just the most direct line, but instead it's more about the total amount of path taken to take from getting from one position to your final destination. So that's the kind of idea that I kind of wanted to mention about. And let's go on to the third example. Well, the third example is the same idea that we're talking about Rn with an Euclidean norm. So what we're just saying is that just now in example 2, we were just talking about a Rn, R2 with your norm, let's say with norm V defined as x plus x2 and y, x2 and square. Well, that's what we see in example 2, right? So it's almost the same idea here. We're just trying to extend it into Rn, and all the things, as we can see, if we have Rn and R4 and up to Rn, each one of the cases for any n will still become a norm vector space. Well, if you think about visually, let's think if we consider the first condition, that let's say we consider the first first condition of being a norm, which we have right here, that the norm has to be a non-negative. Well, then this is going to be applied to the same thing, because in any n dimension, let's say you have R2, then it's always the case that any norm that you're going to take, right, it's going to be non-negative, right? You cannot have any kind of negative value of, you cannot say that, oh, this the norm of this vector is going to be, minus something, some value. It has to be always positive, right? Well, this idea is applied to the same thing. It doesn't really changes, right? That if we take this guy right here to have some position A, B, C right here, well, this guy always, if you take the norm of this guy, right, it's going to be the same. It's going to be always a non-negative value. So that's the kind of idea. So next, what we want to talk about is a metric induced by norm. So what is this trying to tell us is Hi everyone, so we'd like to continue our slide. Now we're going to talk about p-norm. Well, what p-norm is we can define p-norm in this way. And p-norm is a generalized way of measuring the length of a vector in a vector space. And we can set different kind of p to get different kind of way to measure the length of a vector. We can have your taxi norm, you can have your Euclidean norm, and you can have your max norm. And what we say here is that the p controls how vector component contributes to the overall length. So let me just give you an example, like in what kind of situation we'll be using this. So let's say that we want to calculate the cost of fuel for different vehicle. Oh, sorry about that. Vehicle. And let's say that if you're gonna send a Amazon package from, let's say, this position to this position, 3, 4, right here, and then you're gonna use a truck. And before even I tell you what kind of space we're moving around, is that let's say that we have a block of city right here. Then if you want to calculate the total fuel it's gonna need it for the truck to go from 3 to 4, well, you can't basically the truck basically you can't just move across the city because there's no road for it. So what you have to do is you have to make sure that the truck goes in a first direction, and then it goes to the second and move its y-axis direction. So in this case, what we're trying to do is that we're using a taxi norm. Let's say that this vector x right here and y, it has the size of this guy right here has a size of 3 and it has a size of 4. Then if we're using our taxi norm cap right here, then we're using, what we're trying to say is that we're taking the first component and then the second component and then add them together to get a total cost of 7. So that's the first taxi norm. But if I told you that, well, we might have a different way, we might have a different vehicle to transport your package to 3, 4. well, let's say like if we can use a helicopter. Well, in that case, you don't have to really try to move like a truck. You can just directly bypass the city to reach 3-4. Well, in that case, it's not really suitable to use taxi cab norm. Instead, we'll just basically use a Euclidean norm, which we define here. So what we're gonna do is we're gonna take 3, 4, and we're gonna add them to get 5. So that's the kind of different, you see, as we can see, we're basically, the P right here is trying to control how the vector component is contribute to the overall length. So you see this, in this case, we have these total components is contributing to the length, but in the case that if we use helicopter, we're only considering this component right here, which is the shortest distance, right? And well, lastly, I also want to kind of put into what is a max norm is for. Well, max norm, it's kind of more, I couldn't think of like really a good example, but what I kind of thought of is that if you have, let's say, like a drone, let's say that the drone only move in one direction. It can either only move in X direction or it can either move in Y direction, but you can only choose one of them. So in our case, 3-4, if you kind of want to try to make sure that the drone, even it cannot reach to 3-4, you want to make sure that it kind of get closer to 3-4. Well, in that case, you can calculate your max norm, which is your max, which is between, you take your component of 3 or 4, well, then you're gonna get 4. Well, this is kind of indeed true in the visual image, because this component right here is more, it has a larger norm, and the length of size of this vector right here is larger, so you want to take this guy, take the y-axis, and make sure that the drone fly in that direction rather than the x direction. So that's the kind of idea why we're using like different kind of p norm right here. And next, what we would like to talk about is we're going to talk about linear functional. And as you guys know from linear algebra, that I'm pretty sure everyone is familiar with this definition right here. A function transformation from a vector space V to another vector space W is a linear functional if any vectors which is from the vector V and the C from a few, scalar from a few. Then what he's trying to say is that the transformation, if you scalar the vector and then you take the transformation, it's going to end up in the same as the scale. You take the transformation of your u vector and scale it. It's going to be the same result in both sides. Well, this is basically kind of the same idea that you guys see, but in our case, what we're going to talk about linear functional right here is that the difference here is that we have a vector to number map rather than a vector to vector map. And basically, and the domain right here is already fixed to be a non-linear space. Well, you can basically see the same idea in the formal definition right here. As you can see that the domain are already fixed to be a non-linear space, and its function sends it to either numbers, right? So that's the kind of idea of linear functional. And if we talk about the meaning of the linear functional, well, let's look at this example. Well, what linear functional is essentially saying is that we have Well, f is linear. Well, basically what we're trying to say is that the f output itself is growing in a constant rate, right? So let's say that we well, I know that you guys learned in linear algebra that if you need to check something is a linear transformation, what you're gonna do is you're gonna try to, let's say that you want to check your first condition, TCU, and you gotta pull out your definition for your T, and then you have to end up in this side right here. But today I'd like to show you like a different way of like checking this condition. So for example, we have, let's say that we have two different function. We have your f and you have your g right here. Then if you kind of try to plot it into in a 3D space, right here it's gonna be looking like this. Sorry for my bad drawing, but that's the kind of idea. You have your f is a plane right here, and you have your curve plane right here. You have your g right here. Well, you're saying that f, let me just draw, let's say that we take this guy right here and we draw its contour map. And if you guys remember your calculus 3 contour right here, the purpose of contour is that we are trying to measure the height of the, we're basically trying to map the height of the plane for each different location. So right here you have different, basically in this one, right, you have different kind of height. So if you kind of think about this way, maybe let's say you have your, let's say this guy is C1, C2, yeah, different heights, right? So let's say maybe this one right here, it could be 20, or this one it could be 10, it's more. But anyway, that's not the really important point. But what I want to tell you here is that, our point is to just tell you that f is linear. So if you kind of look at each one of these different outputs, right? Well, what you can see is that if you take this guy, if you take this from this position and map it to this, and you check its growth, how much it changed. And by the way, like C is actually an output for the output for your f function, and you can see that your function is growing. Your first output for the function is going to be C1, the second going to be C2. As you can see, the growth right here is, it grows in a constant rate. If you take this guy right here, it's going to be the same rate as this one, right? So, that's the kind of way you can kind of check that whether like f is linear, then you're just checking that f grows at a constant rate. So if you kind of think about, let's say we can think about, well, what kind of example we can think about, like if a function is not linear? Well, that basically applies to the function g. It's because if you look at its contour, right, its contour is going to look like this, right? We have different level of heights, right? And if you pick, let's say we pick a point from here, and you see that you want to check that, the growth, the changes in the growth, the output of g, well, it's kind of differ from every single point. You can see that the first one right here and the second one, it's quite different, right? It doesn't grow at a constant rate. That's why in that case we're trying to talk, we can say that your g is non-linear. So that's the kind of idea we can talk about linear functional. And the third one, now I'd like to talk about the continuity of linear functional. So let's just read the theorem. The theorem states continuity of linear functional. Let f be a linear functional on x, where x is a norm linear space. F is continuous if and only if that the supremum of f, the absolute value of f of x, is less than infinity for all the vectors that has the size, unique length, has a size of 1. Well, so this is kind of a bit difficult to kind of understand, but what it's trying to tell you is that, let me draw a picture to tell you what it means. Well, if you kind of read it from the right side, from right to left, right? And what we got to do first is that we're just taking a vector, right? We're just taking a different kind of vectors. We're taking A, B, C. Each one of them has a unit, has a length of 1, right? This also applies to B and C. And if you take a set of vectors and let's say you map these vectors using a function, and you assume that the function is linear, and you map it, let's say you want to map it into real line, and let's say your non-linear space is your R2, for example, then what it's trying to say here is that you're saying, let's say that we're trying to map f of A and f of B and f of C. You map you map each one of your vectors to the real line, and just give me, let's say that each one of the output is kind of close to each other and growing at a quite constant rate right here, right? And then what is trying to say is that you're saying that the supremum of f of x, it has to be less than infinity. So what we're trying to say that all of these mapping right here is going to be bounded by a supremum, right? So what we're trying to say here that, you know, since that each one of the mapping and its upper bound, its upper bounds, it's going to be supremum is going to be bounded. Well, then we're saying that the output is going to be very close to each other, and it's not going to be having a value that is going to be exploded, and it's a bit far away from these value, right? Let's say that if our, say we have a function mapped to here, it's a bit far away, then we're saying that, oh, the continuity is violated, right? So that's the kind of idea. We take a set of vectors which has a length of 1, we map it into a function, we make sure that the output are quite close to each other, right? And that's going to ensure that our function is going to be continuous rather than being exposed to a value that is far away from the other ones. So that's the kind of idea. And I thought it would be nice to kind of show you a bit about the proof. Hi everyone, so we'd like to continue our slide. Now we're going to talk about the continuity of linear functional. And what this theorem is basically trying to tell you is that it gives you a condition if you have your function is linear and it is on your norm linear space, and basically you can check the function is whether continuous by saying that the supremum of the least upper bound of your function for all the set of vectors that has unique length of 1 is finite. And well, this is a bit hard to think of, but I'll show you a visual way to understand this. Let's say that we start from right side, and if you read it to from right to left, well, what we're trying to say here is that you have a set of vectors A, B, C, and you're trying to map those vectors using your function f, which is linear. And let's say you want to map it, your vectors output to a real line. And what you're trying to say here is that, let's say that we draw each one of our output, and we're talking about it has its upper bound, least upper bound, right? This guy right here is less than infinity, which means all these output are finite, right? In the sense that we can see that each one of the output FA, FB, FC is close to each other, and it's not far away. There's no value that is far away from these guy right here. So if you think about the case that, well, when your function is going to be discontinuous, well, we typically say that if a function and have a break or gap between them, then that's basically a discontinuous function. So, well, in the case you have, let's just say that your supremum, it goes to infinity. Well, that basically you can think of this way, is that you have f of a here, f of b, f of c, and then you may have some value f of m that's closer to infinity, but you may have some value that is a bit quite explode, and it's a bit far away from this. So in a way you can say that all the vectors in the neighborhood of f of m doesn't map close to there's no value that might close to this guy right here. So that's why you can say that this value right here, it explode way towards to infinity. So you can say that the f can be discontinuous. So that's the idea. And I thought it would be nice to give you a proof from right to left. So let's just look at the proof. Well, first of all, if we think of this way, what we gotta show is we have to show f is continuous using the assumption of this guy. So let's just write this. Suppose that our supremum for f of x, the absolute value of f of x for all set of unique length of 1, and set it to m, and m is less than infinity, which means that finite. This value is finite, right? The mapping is finite, sorry. So, and we want to show that f is continuous. Then we write our usual definition, right? That is, for any epsilon that is greater than 0, there exists a delta that's greater than 0, such that if you have your norm of the difference between x minus x0 is less than delta, then we can imply that your f of absolute of f of x minus f of x naught is less than epsilon, right? So basically what we're gonna do, if you guys know that the proof, well, what we usually do is that we have a assumption and we want to try to make sure that we build this guy, and we take this guy right here to relate this so that we can end up to have our inequality on the right side for epsilon. So let's just start the proof. So first of all, let's just start by defining our y to be this guy. And if we take the norm of y, what we get is that we get a norm for this guy right here, and we will get a double we will get a double norm here. And if you guys know that if you taking a double norm is basically taking the norm once, it's the same idea. So we can express this guy into here, so we get the norm of y to be equal to 1, which means that the norm of y the norm of y have a unit length of 1. Then we can now use our assumption, because that our assumption says that the supremum of f of x is less than infinity. So we can basically say that some specific vector that is not the least upper bound is less than equal to m. So in a picture, well, you got in a picture we can say that, well, supremum, right, of f of x, like here, is equal to m. So we can say that any one of these guy right here, f of y is, let's say we can say f of y is here, so it should be less than equal to m, right? So giving your we can define another y right here, and let's say that we want to apply your f on both sides. Then we get your f, you get this guy right here. So what we're gonna do here is you want to use your you want to use the definition of linear functional. So if you guys remember, into this one right here, you see that linear functional, the definition it should look like this, right? So going back to this guy, we have a assumption that we can say that if linear functional, well, we can use this because f is linear functional, so you can apply this guy right here. And what we're trying to do here is that your c is 1 over the norm of x minus x naught, right? Then you apply this equation, so we can take the whole thing out of the function and you get this. Then we use the same idea. We use the second condition of the linear functional, which was, if I'm not wrong, it should look like this. If you take two vectors, you add them, you apply the function, then you result in this guy. What you got to do here is, well, now I'll focus on this guy right here, is that we have f of x minus x naught. We can express this guy as x naught x0. So now we finish expressing this one. we can take your x and your y component and apply your linear functional. Then our result will end up being f of x plus f of x naught. And you can apply your linear functional definition again, since this is minus is just a minus one scalar, so you take your scalar out of the function, which you get a minus f of x naught. So that's what you got here. Then you apply your absolute value to the whole thing right here. Okay, so you apply your f absolute value on both sides, and let me just erase some stuff so to not confuse you. So since we have, let me just erase this one too. So we have this assumption. So we just, because f of y is expressed as this, and we can use the assumption for which is less than or equal to m. Then we multiply both sides by the norm of x minus x naught for this guy. Then what we're gonna end up is this guy right here, which is very, very clearly, you can see that. Then, well, what do we see? We see that this guy right here is our assumption back in here, which is x minus x naught less than or equal to delta. So what you're gonna do is you make your delta here and you get your epsilon. Well, I'm not gonna explain this one because everyone know that that's what we're gonna do. So that's the kind of the proof of your proving that f is continuous and assuming that your supremum of f of x is less than infinity for all set of unit vectors. So what I want to point out right here is that why do we have to use, well, in class, right? Why do we have to use neighborhood instead of sequence for continuity? Oh, it's because the neighborhood captures locality better than a sequence. Or even in vector space, such as like application like wind flow or concept like closeness, it's like better than represented by neighborhood than sequence. So let me just show you what I mean by that. So let's say that if we, well, what I'm trying to focus is that, well, we have our usual f is continuous definition right here. Then f of x is f of minus f of p is less than epsilon, right? If you kind of just focus on this guy, well, in our case, we're defining that as the norm of this, right? But in the same case, you see that neighborhood express your locality better. So for example, in our case, if you have, let's say that you are in a circular room and you are standing in this position x naught, you have a void, and let's say that you want to consider, you want to use a way or expression to express the surrounding vectors that near x naught. Well, then in case if you use a neighborhood, what we're saying is that we are taking the neighborhood of x naught, and every vectors that pointing towards x naught, which you can think of these vectors are wind flow, right? Well, then it in a vector sense, in a vector space context, you can see that each one of these vector, the neighborhood captures the continuity better. So if you, in contrast, right, if you think about, let's say, a sequence, in sequence, well, when I first draw this out, I kind of understand that why neighborhood capture more locality better than sequence is because if you think about, let's say, like a sequence, right, then you're saying the sequence of vectors is converging to x naught. But in this case, we see that it doesn't really capture the locality because your mind tells you sequence, it goes in your, by intuition, it tells you that sequence, it goes in a specific linear path like this, right? But in our case is that you see neighborhood is more considering about the surrounding or the locality. So you see that even in vector space, if you represent these bunch of vectors right here as your wind flow that heading towards your direction, well, sequence there doesn't really capture the nearby wind flow, the idea of wind flow, because wind flow doesn't flow in a sequence manner, right? It's more about it comes in a pack or a bunch, right? So that's the kind of thing I just wanted to point out. So the last one is that we're gonna go about banach space. So before I kind of dive into like very detail of the banach space, well, banach space is basically a norm linear space that's complete. Okay, or we can say that some set is complete, right? Well, but when you say that a norm linear space is complete, then you're saying that then that non-linear space is a banach space. That's kind of like just the difference, Okay, so that's the kind of rough idea. So let me just, before we even, what we're gonna do right now is to understand what is a banach space. So I should tell you what a Cauchy sequence is. And a Cauchy sequence whose terms get closer to each other as the sequence progresses, right? So for example, one specific example, and even if you, one specific example, you can think of a sequence, right? Let's say that's 3 or 3.1 and 3.14, 3.141, dot, and it goes to approaches to pi, but it doesn't. But that's not the point, but we can see that each one of the terms, right, 3.1 and 3.14, 3.14 or 1, each one of them are quite close to each other, right? So that's why it's a sequence that gets closer to each other. Its value is getting closer to each other as your sequence are trying to progress towards a value, right? So if you kind of look it on Google Map, well, what is going to show you? They're going to show you this picture. So what does this mean? Well, it's basically saying the same thing, but it's, we can try to use our example here. Well, it's just basically you have some sequence, a sequence and whose term, right, it's getting closer and closer to a specific value, right? So that's the same idea, but it's just represented in a visual way. Okay, so that's the idea. And the second definition we're going to talk about is the space is whether complete or not. And let's just read through this. Is that a space is complete if every Cauchy sequence within the space converges to a point that is also within that space. So let me just give you an example what is complete. So if you look at your let's say you look at what is complete. If you look at your if you look at the real line, well, you can see that R is complete. So for example, you can take one Cauchy sequence, say a sequence, then go from 1 and it goes to root of 2, right? And you're saying that you have a sequence of values starting from 1 and converges to a point within the space. So your sequence are these sequence right here, and then you want to say that it converges point to square root of 2. Well, square root of 2 is indeed a irrational number, but that irrational number is also a subset of R. So that's why you're saying that the sequence is converged to a point that is also within the space and it's not outside of space. So let me show you what we can consider as a space is incomplete. Is that, well, if you kind of flip this definition, then what we're gonna get is that a space is incomplete if there exists one Cauchy sequence that convert out of the space. Okay, so let's just say that Q is incomplete. Why? It's because Q is a rational. It's all the set of rational numbers. And let's just think about this case, right? We have your Q. Let's say we take 1, and 1 is a irrational number because you can express 1 as 1 divided by 1. And you can have some other values like 4/2. Then you keep getting your value, can be any rational number, and then you see that rational number, for example, it converges to square root of 2, right? But you can see that square root of 2 is not in the rational function. Instead, it's in an irrational. That's why you're saying that the Q is incomplete, because there exists a sequence within the space that converges into a space, converges to a point that is not in the space of Q. So that's the kind of idea. So let's go through this theorem. Well, what this theorem is basically telling you is that you can use Cauchy sequence to describe using vectors. So I just read the theorem. Let X be a norm in a space. A sequence of vectors in X is a Cauchy sequence if and only if the norm between the difference of xn minus xm is gonna converge to 0 as m and n is gonna converge. It's gonna get closer to infinity. So, what does it mean? It means that as the sequence progress, right, the distance between the vectors, it's gonna get smaller and smaller and smaller, and almost becoming 0. Well, this is kind of the same idea we're talking about. It's the same idea what we're just saying is that we're just saying a sequence is, we have a sequence and its term is getting closer and closer as we progress. So let me just show you a visual way to understand this. Let's just say that your norm is R2 and you have a sequence can be defined as 1 over n and 1 over n. Then what we're trying to say here is that, let's say that we try to write out our sequence to further understand what it means, and we have, let's just say our n, we can start from 1, okay, then we keep writing out the couple terms, then that's what we get, 1/4, and maybe we might get xm at somewhere, but you have to understand that xm, the vector xm and xn, these are the vectors that has been progressed quite far away, as we can describe it here. So what we're seeing is that we have a vector x1 and the second vector x2 and the third vector x3, and it gets very smaller. So, and as you can see, well, xm and xn, right, it's very tiny and small, we can't even see it, but what it looks like this, okay? Well, we're just seeing as the sequence of vector progress, we're just saying that these distance, okay, this distance right here, oops, are getting closer to 0, which means approaches to a value. So you see, this is like a way of just describing Cauchy sequence. What we're saying is that well, in the previous example that I show you, you're just saying that each one of the term, right, in a sequence it gets closer and closer, approaches to a value. Well, this is the same idea. We're just saying that each one of the point, right, it gets x2 and x3, each one of the term, it gets closer. But in this case, we have each one of the term to be pointed by a vector. So that's the kind of idea of describing Cauchy sequence with vectors. Then the third one, let's use this, and what we're gonna say is that if the theorem 3 is basically say that non-linear space is a complete space, and that X be a non-linear space, and X is a complete space if and only if every Cauchy sequence in X converges to a specific vector X that is also within the X. Well, this is almost the same as what we say in above, that we're just saying that a space is complete, but we're just using in a sense, we're just using vectors to describe, and that's the idea. So what we can count through is that a non-linear space that is complete is called a banach space. So what we're just saying is that we have a vector space, okay, equipped with a norm function, and we're just saying that this space, the space right here, is complete. Then we can just call that a banach space. That's the kind of idea. I kind of might run out of time to do this, but let me show you like an example of what we can what we're trying to what kind of things objects we're trying to talk about in banach space. Is that we can use this example. So let's say that all the continuous function that's restricted in an interval of a b equipped with the supreme norm is a banach space. Well, I cannot show you the proof of that because it's going to be very long, but well, what it means is that every sequence of continuous function on the interval ab converges to a specific continuous function within the same space. Okay, so well, an example, what kind of things we're trying to do with is that, well, we'll say, let's just take that, you say every sequence, but let's just say like one sequence of continuous function. Say that, well, you can define this to be a sequence of continuous function. Well, and this is basically called, you can also think of it as a way of a Cauchy sequence of parabolas. It's because if you plug the value, right, you will get t squared plus 1, t squared plus 0.5, and then you eventually get t squared if you plug your n values, okay? And you have, let's say you put it in your visual R2, right? You have an interval between a and b, and you're starting from, let's say, you're starting from this guy, t1 plus, and you're starting from, you take your second term, right? And it says that it converges to a specific continuous function within CAP. So it converges to this continuous function, which is our t squared. So that's the kind of idea of what we're trying to say is that every sequence of functions. So we just pick, now what we've done here is we pick a sequence of continuous function on an interval and converges to another continuous function. But this is kind of quite true, because what we're trying to say here is that if you have an interval a and b, you pick any kind of continuous function, right? It can be linear or it can be x, well, that's a bit, let's just draw it clearly. And it can be a linear function, it can be parabolas, or it can be a x cube, right? Well, you see that if you pick any one of them, right, if you pick any continuous function to be the term within the sequence, then it's always going to be converged into a continuous function. That's the kind of idea. And it says, and also I just wanted to mention is that well, we have a equipped with supreme norm. So equipped with a norm defined as this, and that's what we're trying to say here is, well, you have a function, you can take any function, and you can just measure the size of the function. For example, let's just take this guy, right? Well, you see supreme of x, you're just trying to measure the height of the function. For example, if you want to measure the norm of this guy right here, then let's just say that, suppose that if its maximum height or maximum range is this point, and we're just taking the norm is going to be this guy right here, right? So that's the kind of thing we can talk about banach space, is that you have a sequence of a vectors. In our case is a function, the vectors are a function, and this sequence of vectors that comes from a vector space. It and you make your sequence of vectors to be move forward and progress. It's gonna converge to a specific vector that's also come in the same space. In that sense, you can say that the whole space and the norm, it's gonna be a banach space. So thank you for listening to my introduction on norm vector space.